Yes. Now we're going to continue with our operations. We are looking at the third one, and this one would be intersection, okay? The third one would be intersection. And intersection is represented by the symbol N like this. It's like an N, all right? And in English, it would translate to end. It would be end. So let's put a situation of that. Let's say we want to find A intersection B, which we can also read as A and B, right? So what are we going to do? Put our Venn diagram. You should be able to see this on a Venn diagram. So this would be, we could have our set A and we could have our set B like this. Now the intersection is where it is in both A and in B. And that would be this region which we shade. Okay, this is our universal set. And here we have shown A intersection B. Okay, this is the A intersection B, the part which is in both A and in B. Now, in set builder notation, what would this be like? We would say, we would choose some letter to represent. We like to use X, okay? It will say A intersection B is represented by the set of values X, okay? X is the letter that is representing everything in here, all the elements. Then now please tell us what X is. X is an element of A, and X is an element of B. So this is easy because you just should know this word that joins them, and this intersection, okay? So X will be in A and X will be in B. That's how it means, and you would be done. So if you were to look for any situation, you should just make sure that whatever you put in A intersection B is in both. So if we had the last example, let's just say it's 1, 2, and 3. These are the guys in here. And let's say in B we have 3, 4, 5, 6, 7. So now if we say, what is A intersection B going to be? It's just something which is both in A and in B. So we check 1. Is 1 also in B? No. 2. Is 2 also in B? No. 3, the next letter, is the next number. Is it in B? Yes. So we can put it. So this would just be 3. And you are done. You don't have to try 5, 6, 7 because they are not even in A. So you're wasting your time. Okay. Now this would be it. And then you may have this fourth one. Now let's talk about the fourth one, the fourth set operation, and that is difference. Okay. That is difference. And it is, we'll show it as A minus B. Okay. A minus B. Let's put it on a Venn diagram. Here's your Venn diagram. This is our universal set. We have set A. Oh my gosh, let's say something before I leave this. There's a situation that I'm forgetting. And that is a situation that comes in intersection. That's a special situation. And that is the idea of, I always forget it, it's the idea of disjointed sets. Okay? This is the idea of disjointed sets. So I'm going to take this down so that I can be able to show you the idea. All right? I'm going to move this down a bit. We'll come back to it. So we want to talk about the idea of disjointed sets. Under intersection, there is the idea of disjointed sets. What is this idea all about? The idea of disjointed sets. When we say we have disjointed sets, we are saying they have nothing in common. We have sets that have nothing in common. So for disjointed sets, this is the condition. Okay, if we were to see it on a Venn diagram, it will be sets that never ever meet. They have nothing in common. This will be A and B. So when we have disjointed sets, it means that A intersection B is nothing. It is an empty set. So you can write it in this way, or you can say that A intersection B is equal to this symbol. Nada. Empty set. Remember, you don't join the two things. All right. So when A intersection B is equal to nothing, we say we've got disjointed sets. Sets that don't come together. They have nothing in common. And the property that comes from this thing, the property that comes from these disjointed sets is to say that if I say A minus B for disjointed sets, if I say A minus B, first let's talk about difference maybe. Difference, then we'll come back to this. When we have A and B like this, where we have our A here, we have our B, it's our universal set. If we say we want A minus B, we are saying that it should be in A, but not in B. So we will be, if we say A minus B, means we are looking at A, but we should remove B from that. Do you get the idea? we are looking in A, but we are going to remove the part which is also in B from A. So we will take A, we will be taking A, but we'll leave the part which is in A and also in B. So we'll be leaving that part, okay? So we are removing B from A. We are taking the whole of A, but we are removing the things which are also in B. So if we are to represent this in set builder notation, we would say these are X such that X is an element of A and X is not an element of B, okay? It should be in A, but not in B. And how we would get it is if we just have the sets A being, let's say A is 1, 3, 5, 7, 9, and then set B is 4, 5, 6, 7, 8, and 9. Now, if we were to say, what is the set A minus B? So A minus B, here's what we do. It means we are looking in A, but we are removing the things that will be in B also. So we start from A. We will just be trying to see if that thing is in A. We'd start with 1. Is 1 also in B? No, so 1 can come. We'd go to the next one, 3. Is 3 also in B? No, so 3 can come. We go to the next one, 5. Is 5 also in B? Yes, so it can come. 7. Is 7 also in B? Yes, so it can come. 9. Is 9 also in B? Yes, so it can come. So this is your answer of A minus B, all right? Now, for disjointed sets, to say A minus B, you are saying we are taking from A, but we are removing the part which is also in B. And guess what? There is no part which is also in B because they don't come together. So for disjointed sets, it means that A minus B will just be A. Okay, removing B does not change A because A has nothing in common with B. So if you see A minus B giving you A again, this simply means you have disjointed sets. It means A intersection B is nada. You have disjointed sets. Please know that, all right? That's it. Bye.